And welcome to this lecture on Azure Firewall. Azure Firewall is a managed stateful firewall appliance which protects Azure virtual networks. Three types of firewall rules can be configured: network address translation or NAT rules, network-based rules working at layers 3 and 4 of the OSI model, and application rules working at layer 7. Microsoft Threat Intelligence feeds are integrated to Azure Firewall, with lists of known malicious IP addresses and domain names that can then be incorporated to rules. Azure Firewall is highly available and fully scalable. A recommended architecture for Azure Firewall is shown in this diagram. The Azure Firewall sits in its own subnet within a hub virtual network, and more than one spoke virtual networks within Azure connect to it. And also there are connections from the hub VNet back to on-premise as well. By default, all traffic from the Azure Firewall is denied, and then optionally allowed based on rules. Traffic filtering can take place between the hub VNet and the on-premise network. So now it's time for the Azure Firewall Lab. Use the virtual network and virtual machines from the NSG lab, after you've turned them on of course. Create the Azure Firewall subnet within the VNet, and the name has to be exactly that. Create the Azure Firewall with a public IP address. After configuration, you'll have three separate subnets within your virtual network: the front-end subnet with the Bastion and a public IP address, the back-end subnet with the Linux server and no public IP address, and then the Azure Firewall subnet with your Azure Firewall and its public IP address. Route the traffic from the back-end subnet to the Azure Firewall. Create a route table. Set up the default route to the private IP address of the Azure Firewall, and then associate that route table with the back-end subnet. Create rules to allow UDP 53 for DNS to 8.8.8.8. That will be a network rule. And an application rule to allow HTTP and HTTPS to www.google.com. Then test. Remote desktop to the front-end Windows virtual machine, as you did before. From the Windows server, SSH to the back-end Linux virtual machine. On the Linux virtual machine, test the DNS rule by typing in the command dig www.microsoft.com, and then a space followed by @8.8.8.8, indicating the IP address of the DNS server which you want to use. Then try a different DNS server, which should fail. Also on the Linux virtual machine, test the Google rule. Use curl https ://www.google.com. That should work and provide a response. Then try curling to a different domain name, which should fail. When you're finished the lab, keep the virtual machines and networks because you'll need to use these in later labs. However, shut down the virtual machines to minimize spend. And destroy the Azure Firewall, route table, and the public IP address of the Azure Firewall as well. If you would like to take the challenge approach to this lab, then please pause the video now. Go ahead, follow the steps as detailed in the video, and when you're finished, you can compare how you did it with my walkthrough. If you'd like to take the guided approach, or you just want to watch this as a demonstration, then I'll see you in the Azure portal now. So here we are in the Azure portal. Begin by heading over to Virtual Networks, choose the EastUS virtual network that you created in an earlier lab. Select Subnets, and add a new subnet. The name of the subnet has to be exactly Azure Firewall Subnet. The address range should be 10.10.6.0/24. We won't apply a network security group or route table, and we also don't require service endpoints. The Azure Firewall subnet has now been created. Next, select Firewall. Add a new firewall. Call it app EUS for EastUS FW. Select the EastUS region. Use the existing virtual network. Create a new public IP address, and review and create. After validation, press create again. The deployment of the Azure firewall is underway. I'll fast forward the video until it's complete. And after 5 to 10 minutes, the deployment of the Azure firewall is complete. Go to Resource, select Rules, go to Network Rule Collection, and add a new Network Rule Collection. Call the Network Rule Collection Allow DNS. The priority you can choose. You can name the rule Google. Protocol UDP. Source address, we'll leave it any. Destination will be 8.8.8.8. And destination port will be 53 for DNS. Press Add. And refresh to see the rule. Select Application Rule Collection. Add an Application Rule Collection. Call the Application Rule Collection Allow Search. Give it a different priority from the previous rule. We're not going to use fully qualified domain name or FQDN tags in this lab, however, it is interesting to look at their functionality. Microsoft provide and manage a set of domain names that together make up commonly used services in Azure, such as Windows Update or HD Insight. For the target FQDN rule name, call it search. Source addresses should be star for any. Protocol and port should be HTTP, HTTPS. Target FQDNs should just be www.google.com. And add. The application rule collection has now been added, and the next step is to ensure that the backend subnet routes through the Azure firewall. Select Virtual Networks, choose your East-US virtual network. You should now see 3 network interfaces. The first, in my case, is the Linux server connected to the backend subnet. The second, the Windows Bastion server on the front-end subnet, and the Azure firewall on the Azure firewall subnet. Copy the IP address of the Azure firewall to your clipboard. Search for root table. Add. You can call your new root table app -eus -rt. Select the same resource group as before. Location should be East-US. And create. The root table has now been deployed. Select root. Add a root. You can call the root default root. Address prefix should be 0.0.0.0/0. Next hop type should be virtual appliance. And the next hop address you can paste in from your clipboard. That's the private IP address of the Azure firewall. Press OK. The new root has been added. The next step is to associate this root table with the backend subnet. To do this, go back to Virtual Networks. Select the subnets within your virtual network. Choose the backend. Under root table, select your newly created root table. And save. You've created and configured Azure Firewall. Before testing, let's have a look at what you've actually set up. Go to Virtual Machines, choose the Linux virtual machine in your backend subnet. Go to Networking under Settings. And first, take a look at topology. Azure automatically creates a graphical representation of your resources and shows how they're connected together. Go back to Networking, choose the network interface, and select Effective Routes. Personally, I find the effective routes in Azure a really useful way of helping to troubleshoot connection issues. Remember that with a route table, it's always the most specific route that wins out when deciding which way to send a particular packet, unlike firewall rules which are in order. All the routes with a source of default are created by Microsoft based on our configurations. So, for example, the first route here at the top allows any subnet within the virtual network to communicate with any other subnet. The default route to the internet is now invalid because we've put our own user-defined route in place to the virtual appliance, namely the Azure firewall. These other routes are a result of implementing service endpoints to Azure SQL and storage. And the last route in the table is the peering route to West US. So now it's time to test your firewall rules. Remote desktop into the public IP address of the Bastion Windows server in the front-end subnet. I'll see you on the Windows server. We've logged into our Windows server using remote desktop. You may have noticed that the public IP address will have changed if you shut down and then restarted the virtual machine. Before starting, quickly head back to the portal for a minute and just copy the private IP address of the Linux virtual machine to your clipboard. Start PowerShell and SSH to your username at and paste in the private IP address of the Linux server. Select Yes to continue and enter your password. You have now SSH'd onto your Linux virtual machine in the backend subnet. Begin by testing the DNS rule. Type dig www.microsoft.com space at 8.8.8.8. You've successfully received a reply. That's great. That shows the firewall rule worked. Let's just make sure that it blocks other IP addresses used for DNS. Press the up arrow and change the last two octets to 4.4. That's another DNS server managed by Google. Press enter. And after a short while, you should receive a message that the DNS server cannot be reached. Now test your application rule. Type curl https://www.google.com. And we successfully receive a reply from Google. OK. Control-C just to return to the left-hand side of the screen. Up arrow. And now let's replace that with www.microsoft.com. And you can see that the connection failed. You've successfully tested both the rules that you set up on your Azure firewall. Well done. There's one more thing we need to do, and that's tidy up. Go back to the Azure portal, go to Virtual Networks, Subnets, and choose the backend subnet. We need to disassociate the route table so that we can then delete it. Press Save to update. Then head into Resource Groups, choose the app VNet RG resource group, select the firewall's public IP address, and the route table. Press Delete. Check your selected resources and type Yes to confirm. Your resources are now being destroyed. Next, go to Virtual Machines, select your virtual machines, and stop. Don't delete them because you will need them for later labs. Well, that concludes the Azure Firewall lab. If you have any questions, please let me know. Otherwise, feel free to move on to the next lecture. Hello Cloud Gurus and welcome to this lecture on Azure Front Door. Azure Front Door is an application delivery network with global HTTP load balancing and instant failover, SSL offload and application acceleration at the edge close to end users, and Web Application Firewall or WAF and Distributed Denial of Service or DDoS protection. Azure Front Door Service enables you to define, manage and monitor global routing for your web traffic by optimizing for best performance and instant global failover for high availability. Front Door works at Layer 7 or HTTP/HTTPS and uses the Anycast protocol with split TCP and makes use of Microsoft's global network for improving global connectivity. Azure Front Door provides SSL offload, optional caching, and application acceleration at the edge to ensure low latency to end users around the world. Front Door backends refer to the hostname or public IP address of your app, which can serve client requests. Backend pools are logical groupings of your app instances around the world that are intended to receive the same type of application traffic. An Azure Front Door backend can be Azure Storage, Azure App Service, Azure Kubernetes Service, Azure Virtual Machines, or any other internet-facing HTTP or HTTPS endpoint. Azure Front Door performs health checks on backend resources, looking for an HTTP 200 OK message. If there's no reply, or if a response code such as 503 service unavailable is returned, then the backend will be marked as down, and traffic will not be routed to that backend until the health check status returns to normal. You can route traffic in Azure Front Door based on latency, priority, waiting, or session affinity. When an Azure Front Door is created, you assign a globally unique name, which then forms part of its fully qualified domain name ending in .azurefd.net. A custom domain name can be created and mapped to Azure Front Door using a CNAME. If the website uses HTTPS, this requires an SSL certificate for the custom domain name. You can set up URL-based routing. For example, /login can be routed to a login application, /shop can be routed to a shopping cart application, and /checkout can be routed to the checkout and credit card processing application. To use HTTPS traffic with your own custom domain name, Azure Front Door requires an SSL certificate, for which there are two options. The Azure Front Door Managed certificate is free, or to be more accurate, included in the cost of Front Door. It doesn't support wildcard or Apex domains. acloud.guru, without the www, is an example of an Apex domain, also sometimes referred to as a root or naked domain. The Azure Front Door Managed certificate is not exportable. The second option is to bring your own certificate, which must be stored within Azure Key Vault. Azure Web Application Firewall or WAF on Azure Front Door provides centralized protection for your web applications that are globally delivered using Azure Front Door. It's designed and operated to defend your web services against common exploits and vulnerabilities, and to keep your service highly available for your users, in addition to helping you meet compliance requirements. WAF on Front Door is a global and centralized solution. It's deployed on Azure Network Edge locations around the globe, and every incoming request for a WAF-enabled web application delivered by Front Door is inspected at the network edge. For example, SQL injection and cross-site scripting attacks can be blocked, people who are using the application as intended are allowed through, while web crawlers and malicious bots can be blocked. After the traffic's been inspected, it's forwarded on via the Microsoft Global Network to services in Azure regions, and via the public internet to other clouds and on-premises servers and applications. This allows WAF to prevent malicious attacks close to the attack sources before they enter your virtual network, and offers global protection at scale without sacrificing performance. A WAF policy can be easily linked to any Front Door profile in your subscription, and new rules can be deployed within minutes, allowing you to respond quickly to changing threat patterns. The global WAF policy consists of two types of security rules: custom rules that are authored by the customer, and managed rule sets that are a collection of Azure managed pre-configured rules. Custom rules are always processed first before evaluating traffic against the managed rule sets. A wide range of custom WAF rules can be created. These include allow and block lists for IP addresses and networks, supporting both IP version 4 and IP version 6. Geographic access control based on client IP address, so that traffic from certain countries or regions can be allowed or blocked. Custom HTTP request rules can be created, for example based on HTTP request parameters such as URIs, query strings, headers and the request body, or rules based on the HTTP request method such as GET, POST, PUT or HEAD. Rate limiting rules can be implemented to limit abnormally high traffic from a single client IP address, and these can be combined with match conditions such as HTTP parameters for more granular control. Azure Web Application Firewall on Azure Front Door includes centrally managed rule sets, for which rules are updated as needed by Microsoft to protect against new attack signatures. The Azure Managed Default Rule Set provides a range of protection, including against cross-site scripting, SQL injection attacks, remote code execution, local file inclusion, and protocol attacks. A managed bot protection rule set can be enabled for your WAF to take custom actions on requests from known bot categories. There are 3 bot categories supported: bad bots, good bots, and unknown bots. Bot signatures are managed and dynamically updated by the WAF platform. Malicious IP addresses for bad bots are sourced from the Microsoft Threat Intelligence feed. Azure DDoS protection combined with application design best practices provides defense against distributed denial-of-service attacks. Azure DDoS protection is offered in 2 service tiers, Basic and Standard. The Basic tier is free, whereas the Standard tier has a monthly charge and a usage element. Both the Basic and Standard tiers provide real-time traffic monitoring and mitigation against common attack types. There's no service level agreement or SLA in the Basic tier, however an SLA is provided in the Standard tier. Metrics and alerts on DDoS attacks are available only for Standard tier, as are logging and reporting. The Standard tier enables access to the Microsoft DDoS response team, as well as service credits in the case of an app scale-out due to DDoS, which would normally incur additional costs for app services resources. Distributed denial-of-service or DDoS attacks are some of the most significant availability and security concerns facing customers who are moving their applications to the cloud. A DDoS attack attempts to exhaust an application's resources, making the application unavailable to legitimate users. DDoS attacks can be targeted at any endpoint that's publicly reachable through the internet. DDoS Protection Standard can mitigate several different types of attacks. Volumetric attacks, which aim to flood the network layer with a substantial amount of seemingly legitimate traffic, including UDP floods, amplification attacks, and other spoof packet floods. Protocol attacks, which can render a target inaccessible by exploiting a weakness in the Layer 3 and Layer 4 protocol stack. Examples include SYN flood attacks, reflection attacks, and other protocol attacks. And application layer attacks, targeting web application packets to disrupt the transmission of data between hosts. Examples include SQL injection, cross-site scripting, and other Layer 7 attacks such as HTTP protocol violation. The application level protection feature of Azure DDoS is provided through its integration with Azure Web Application Firewall. Well, that wraps up this lecture on Azure Front Door. If you have any questions, please let me know. Otherwise, feel free to move on to the next lecture. Hello Cloud Gurus and welcome to the Azure Front Door Lab. You will require a registered domain to complete this lab and the ability to set DNS records. Begin by viewing the AZ-500, a Cloud Guru GitHub repository. You'll find the link to this in the resources section for this lecture. Follow the detailed instructions in the Front Door folder README. Create static websites on storage accounts in Australia, Europe and the USA. You'll then create an Azure Front Door and backend pool. Create a custom domain with an SSL certificate and view the website using that custom domain. Then implement Azure Web Application Firewall and create a policy and test. When you're finished, tidy up by destroying the Azure Front Door storage account and Web Application Firewall policies, and delete your DNS record. If you would like to take the challenge approach to this lab, please pause the video now, go ahead and complete the steps as detailed in the GitHub repository, and when you're finished, you can compare how you did it with my walkthrough. If you prefer the guided approach, then I'll see you in the Azure portal now. You've logged into the Azure portal. Begin by opening Cloud Shell with the PowerShell option. Once you've logged into Cloud Shell, move to your home Cloud Drive directory. Check the contents. If you already have the AZ-500 repository cloned, then cd into it now. Otherwise, just clone the GitHub AZ-500 repository. You'll find the link to this in the resources section for this lecture. cd into the AZ-500 repository. Then cd into the front-door folder. Once you're inside the AZ-500 front door folder, take a look at the script that you're going to run by typing code .. to open Visual Studio Code within your Cloud Shell portal. Select the front door -security PS1 script. Take a look. You'll see that the script begins by creating a resource group called front-door-rg, and then creates a storage account in the Australia Central region to use as a backend, enables a static website on that storage account, and uploads some content. Then the script repeats the process to create a static website on a storage account in the East US region, and finally the West Europe region. Now that you've seen what the script consists of, run the script by typing /front-door-security.ps1 and press enter. At this point, I'll fast forward the video, so you may want to pause the video now and then press play again once your own deployment has completed. The script has now completed and built the resource group with 3 storage accounts. So next, take a look at those storage accounts within the Azure portal. Close the Cloud Shell window. Go to Storage. You'll see that there are 3 storage accounts, starting app AUC, app EUS, and app WEU, each with a random string to ensure that the names are globally unique. For each of the storage accounts, go into the storage account, then go down to Static Website. On the static website, you'll see that the static website is enabled and that there's a primary endpoint, which you can copy to the clipboard, open a new tab, paste and go to that site. Hello Cloud Gurus from Australia. Next, go to the storage account in the East US region. Repeat the process in another new tab. Hello Cloud Gurus from the US of A. And finally, let's go to West Europe. Open your storage account, go to Static Website, copy the primary endpoint, and in the third tab, Hello Cloud Gurus from Europe. Return to the Azure portal, go to Front Door. At Azure Front Doors, press Add. The Create a Front Door wizard will now open. Choose the new front door -rg resource group. Press Next, Configuration, and begin with step 1, adding a front-end host. Press the plus sign. Create a globally unique front-end name. In my case, I'll choose ACG app. For now, leave Session Affinity and Web Application Firewall as disabled, and press Add. Now that you've configured your front-end host, press plus to add a backend pool. Give your backend pool a name. Add a backend. For the backend host type, select Custom Host. Go to your tab with the Australia name. Just copy the domain name. Paste it in. Press Add. Add the second backend. Select Custom Host. Go to your East US storage account. Paste in the fully qualified domain name. Press Add. Add the third backend. Custom host again. Go to your West Europe tab. Copy the domain name. paste it into the backend hostname, press add, and now that you've added your 3 backend hosts, press add to add the backend pool. You've now added the front-end hosts and the backend pools, and the next step is to add a routing rule. So press the plus sign, give the routing rule a name, leave all the other settings as default, and press add to complete the 3rd step. To complete your front door creation, press review and create. Once the validation has passed, press create. Your Azure front door is now being created. This may take a few minutes, so I'll fast forward the video now, and you may want to just press pause and then go ahead and press play once your own deployment is complete. Your front door deployment is now complete, so go to the resource, copy the front-end host URL to the clipboard, open another new tab, and go to that. Hello Cloud Gurus from Europe. By the way, if you don't see this straight away, then just give it 5 minutes or so and try again, because I have noticed that occasionally it takes a few minutes for the application to actually be visible through front door. Anyway, you'll see that one of the 3 storage accounts has been chosen at random by Azure Front Door. In my case, I'm connecting to the Europe storage account. But what if I want to ensure that I always see the Australia storage account unless there's a problem with it? In that case, go to Azure Front Door, open Front Door Designer, open your backend pools. You'll see that the priority of all 3 storage accounts is currently set to 1. The priority within a backend can be set from 1 to 5, where 1 is the highest priority and 5 is the lowest priority. So to select a particular storage account, for example Australia as the primary, open your East US storage account, change the priority to 5, and update. Similarly, go to your West Europe storage account, change the priority to 5, and update. So your Australia storage account is now the highest priority, so therefore the primary. If that fails or is unavailable, then Front Door will then route the application traffic to either the East US or the West Europe storage account. Press Update to update the backend pool, and then press Save to apply. Your updated front door configuration is now being saved. Now that your front door configuration has been updated, return to the tab in which you're accessing the application via Azure Front Door and refresh. Hello Cloud Gurus from Australia. And if this doesn't come up straight away for you, then don't worry, just follow that favourite Azure rule, which is go away, have a cup of tea or coffee, come back after 5 minutes, and try again. Your next step is to add a custom domain, so go to the portal in which you can make DNS changes to your custom domain. In my case, I use Amazon Web Services, Route 53, so I will create a record set, in my case called global.learnsecurity.cloud. The type should be a canonical name or CNAME, and the value should be the name of the Azure Front Door. Once you've pasted in the value and got rid of any trailing HTTPSs and forward slashes, press Create. Your CNAME has now been created, so go to the Azure portal, go into your Azure Front Door resource, open Front Door Designer, press the plus sign on front-end hosts, enter your custom domain name. Your custom hostname should be validated now that you've created the matching DNS record. Enable the HTTPS protocol for that custom domain. Leave the certificate management type as front door managed, and for now leave the web application firewall and session affinity as disabled. Press add. You'll see a warning that the global.learnsecurity.cloud is missing a default route path for both the HTTP and HTTPS protocols, or the equivalent for your own custom domain. Enter your routing rules. At front-end hosts, press the down button, select your new custom domain and update the routing rule to include your new custom domain. Ignore the fact that the errors may still show and press save. Your Azure front door configuration is now being updated, which will include the custom domain and a custom SSL certificate managed by Azure Front Door. To monitor progress, just press on the notifications icon. The custom HTTPS configuration is now being updated. This is a global deployment, so may take around 15 minutes. So I'll fast forward the video, and you might want to pause the video at this point and press play once your own HTTPS configuration has been updated. Your custom HTTPS configuration has now been updated. Test by opening a new tab. Go to https:// and then your custom domain name. Hello, Cloud Gurus from Australia. Take a look at your certificate, which you'll see has been issued with your custom domain name. Now that you've created your custom domain name and SSL certificate managed by Azure Front Door, return to the Azure portal and go to Web Application Firewall Policies. Press Add. Create a new WAF policy. Select Global Web Application Firewall for Front Door. Use the existing Front Door-RG resource group. Give your policy a name. Leave the policy state as enabled. Press Next Policy Settings. Change the mode to Prevention. You can redirect your users to a particular URL if you have a message which you want to pass to them if their traffic has been blocked. Press Next, Manage Rules. Under the Manage Rule Sets, your default rule set will be selected. Also choose your Microsoft Bot Manager rule set. Press Next, Custom Rules. Add a custom rule. Your custom rule name can be called Block Country. Leave the status as enabled. Assign a priority to the rule. This is a numeric value, such as 100. The condition should be geolocation, and for the country code, select your own country. In my case, that's the United Kingdom. And leave the condition as deny traffic. Press Add. Press Next, Association. Add a front-end host. Select your front-end hosts, both the direct domain name for Azure Front Door and your custom domain name. Press Add. Review and create. And once validation has passed, then press Create. Your Web Application Firewall policy is being deployed. You should expect this to block your traffic, as it will detect your country based on your source IP address. Your WAF policy deployment has now succeeded. Go to the resource. Your front door WAF policy can be seen. You can check the policy settings, manage rules, custom rules, and associated front-end hosts are all as you entered during the wizard. Test your Web Application Firewall policy by firstly going to your tab, where you're going directly to the Azure Front Door. Press Refresh, and you'll see that a message is received saying the request is blocked. Go to your custom domain name and refresh, and again the request is blocked. Of course, in this case, if you go directly to the storage accounts, these are not blocked at all. And this does highlight a potential security issue when using services such as Azure Front Door or other content delivery networks with Web Application Firewall policies, and that is that it's important to prevent users from directly going to the end locations such as storage accounts, virtual machines, or Kubernetes services, and then bypassing the Web Application Firewall. That can be achieved using appropriate network security group settings in the case of services such as Azure Kubernetes Service or Azure Virtual Machine. Well, that wraps up the Azure Front Door Lab. There's one more thing to do, and that's tidy up. Return to the Azure portal, Resource Groups, select your Front Door-RG resource group, and delete the resource group. Enter the name of the resource group, Front Door-RG, to confirm, and delete. Your Azure Front Door resources are being deleted, And once that's done, don't forget to delete your DNS record. If you have any questions, please let me know. Otherwise, feel free to move on to the next lecture. Hello Cloud Gurus, and welcome to this lecture on Network Watcher. Network Watcher is a built-in Azure service, allowing you to monitor, diagnose and gain insights to your network performance and health. It allows you to trigger packet captures automatically by setting alerts and gain access to real-time performance at the packet level, with no need to log in to virtual machines. You can gain insights into your network traffic using Network Security Group flow logs, and diagnose VPN gateway connectivity issues. Network Watcher allows you to collect Network Security Group flow logs and analyze them using traffic analytics. You can also collect NSG diagnostic logs relating to rule counts and firewall events such as accepted and blocked traffic. Network Watcher has a suite of built-in monitoring, analysis and diagnostic tools. IP Flow Verify allows you to query whether a particular traffic flow will be allowed or blocked by NSG rules. For example, you may be troubleshooting why HTTPS traffic from one application server isn't arriving at another application server. Insert the IP addresses of the remote and local virtual machines and the source and destination ports and press check. In this case, the traffic is blocked by the rule Deny All In within the Network Security Group app EUS NSG. IP Flow Verify can be really useful for troubleshooting connectivity issues, and it can save a lot of time, as you don't need to analyze the NIC and subnet NSGs, which may be associated with the source and target virtual machines. Packet capture is a way of investigating network issues in great detail by inspecting each network packet using an application such as Wireshark. Packet captures can be initiated via the portal, using Azure PowerShell or the REST API, and written to a storage account, or as a file on the target virtual machine, or both. There are specific connectivity requirements needed to allow Network Watcher packet capture to work. I've put the link to Azure documentation on packet capture into the resources section for this lecture. Effective Security Rules is another Network Watcher tool for NSG rule analysis. This is likely to be particularly useful if you're using both NIC and subnet NSGs. Choose a virtual machine and an interface, and the tool will return details of which NSGs apply and detailed inbound and outbound rules. And now it's time for the Network Watcher Lab. Ensure that you've already completed the NSG lab. This will have left you with a VNet, 2 virtual machines in separate subnets, and a single NSG with application security groups. All of these resources are required for this Network Watcher lab. Start by checking the status of Network Watcher, which you should find has automatically already been enabled in the East US and West US regions. Then, create a storage account in the East US region for log collection. And create a log analytics workspace, also in the East US region. Enable flow logs for East US network security groups. And also enable traffic analytics. Turn the virtual machines on if needed, and generate traffic between the 2 virtual machines. And then view in-traffic analytics. If you'd like to take the challenge approach to this lab, then please pause the video now, go ahead and complete these tasks, and when you're finished, you can compare how you did it with my walkthrough. If you prefer the guided approach, then I'll see you in the Azure portal now. Here we are in the Azure portal. Start by going to Storage Accounts, Add, select the same resource group as before, give a name to the storage account, bearing in mind that all storage account names must be unique. We'll leave it at Storage General Purpose v2, change the location to East US. We only require locally redundant storage. Review and create. And the storage account has now been deployed. Go to Resource, and next search for Log Analytics Workspaces. Add a new workspace, Bear in mind that each Log Analytics workspace name has to be globally unique across the whole of Azure. In my case, I'll use app-eus-la as that's available. In your case, just choose something similar with some arbitrary letters and characters to make sure that it's unique. We'll continue to use the same resource group and put it into the East-US location, leave the default pricing tier. The Log Analytics workspace is now being deployed, and now it's complete. Next, let's look at Network Watcher. The status of Network Watcher can be seen to be partially enabled. That's because Azure automatically enables Network Watcher for any region in which there's a virtual network. You should have virtual networks in both East US and West US from the VNet Peering Lab. So Network Watcher will be enabled in these regions. However, all other regions should be disabled. Moving to Network Security Group flow logs, we only have one Network Security Group, and the NSG flow log status is currently disabled, as is the Traffic Analytics status. Select the Network Security Group, change the flow log status to on. We'll go with version 2, as that includes additional information. Set the storage account to the one which you just created. Increase the retention in days appropriately. I'd suggest 30. Also enable Traffic Analytics. For this lab, reduce the processing interval to 10 minutes and select the Log Analytics workspace which you just created. Save. Refresh. Both the Network Security Group flow log status and the Traffic Analytics status should be shown as enabled. Next, generate some traffic between the virtual machines. For this, you'll need to remote desktop back into the Windows virtual machine. So I'll see you on the Windows server. Here we are on the Windows server. Begin by opening PowerShell and see if you can ping the Linux virtual machine in the backend subnet. As expected, that's blocked by the Network Security Group rule. Control-C to cancel. Next, SSH. Use your username at the IP address of your Linux virtual machine. Enter your password. And you've now logged into the Linux virtual machine on the backend subnet. Let's generate some traffic. curl https://acloud.guru. Well, it doesn't look quite as good when you're doing it via curl. If you didn't get a response, then just check your backend subnet and see if you still have the route table from the Azure Firewall lab associated with it, and if you do, disassociate and delete the route table. Next, let's try pinging the Windows server. As expected, that times out, because there's no rule to allow that. And now it's time for you to return to the Azure portal to take a look at some of the traffic you've generated. Here we are in the Azure portal. Start by going to Storage Accounts. Select your NSG Flow Log storage account. Look at blobs. A container has been generated. If you drill down, always picking the bottom choice, then eventually we'll get to some logs. And as it's version 2, these should be in JSON format. If we edit the blob in JSON format includes all the information on every packet whether it's accepted or blocked, the IP addresses, ports, and how they're matched to the firewall rules. Next, go to Network Watcher. Traffic Analytics. And you'll see a visualization of your traffic. If this doesn't show up straight away, then just wait a few minutes, bearing in mind that the refresh cycle is set to 10 minutes. We can see allowed, blocked, benign and malicious traffic. Moving down to your environment, we can look at a world map to visualize the traffic. View subnets. Looking at the subnet visualization, we can see the subnets in use and the direction of traffic flow. For example, the traffic direction is from the front end to the back end, which is to be expected because we RDP'd into the front end from our laptop and then from the Windows Bastion server to the Linux server via SSH. Going back to traffic analytics, moving down to traffic distribution, you'll see details of malicious traffic, blocked traffic, and frequent conversation pairs. Network Watcher has a suite of useful network diagnostic tools, including packet capture, VPN troubleshooting, and effective security rules. That concludes the Network Watcher lab. If you have any questions, please let me know. Otherwise, feel free to move on to the next lecture. Hello Cloud Gurus and welcome to Network Security Exam Questions. Here are two example AZ-500 exam questions. The skills measured are in the section Implement Platform Protection within the AZ-500 Microsoft Exam Blueprint. Allow 3 minutes per question and have paper and pen ready. For your first question, please pause the video now, allowing yourself 3 minutes to answer. Hello Cloud Gurus and welcome to this lecture on virtual machine security. This section of the course covers an important skill area for the AZ-500 exam, Implement Platform Protection, Host Security. A solid understanding of Azure virtual machines is assumed, to the level covered in AZ-103 or the AZ-900 certifications. We'll begin by covering the Microsoft Shared Responsibility model for cloud computing, then move on to talk about best practices for Azure virtual machine security. We'll cover endpoint protection, virtual machine security at the platform level, Center for Internet Security benchmarks for hardened operating systems, and the use of managed identity for a virtual machine to access other resources within Azure. The Microsoft Shared Responsibility model for cloud computing describes the division of responsibilities between Microsoft and the customer making use of its cloud services. The level of responsibility assumed by the customer varies according to the type of cloud service used, whether it's infrastructure as a service or IaaS, platform as a service or PaaS, software as a service or SaaS. In the case of virtual machines, the customer assumes a high level of responsibility. While Microsoft is responsible for the physical host, network and data center and the underlying cloud service fabric, it's the customer responsibility to keep the operating system up to date, ensure adequate network controls, make sure that applications running on the virtual machines are secure, to look after identity and directory infrastructure, as well as access control and user accounts. Microsoft have published best practice security for infrastructure as a service workloads in Azure. I've put the link into the resource section of this lecture. The first best practice guideline is to protect virtual machines using authentication and access control. Then, use multiple virtual machines for better availability, protect against malware, manage virtual machine updates, manage virtual machine security posture, monitor virtual machine performance, encrypt virtual hard disks, and restrict direct internet connectivity. Starting with endpoint protection, Microsoft Anti-Malware for Azure Virtual Machines is a free real-time protection service that helps to identify and remove viruses, spyware and other malicious software. It generates alerts when known malicious or unwanted software tries to install itself or run on Azure systems. Features include real-time protection, scheduled scans, malware remediation, signature updates, and event collection. Install Microsoft Anti-Malware either using an Azure Virtual Machine extension or Azure Security Center. Third-party anti-malware services are also available, and these cover, in many cases, both Windows and Linux virtual machines. Examples include McAfee and Trend Micro, both of whom have offerings within the Azure Marketplace, and options ranging from infrastructure as a service to completely cloud-based solutions. To ensure effective virtual machine security at the platform level, implement all of the different aspects which we covered in the network security section of this course. Divide virtual networks into subnets for different security zones, and ensure that each virtual machine is placed into the appropriate subnet depending on their function. Avoid public IP addresses assigned to virtual machines wherever possible, and override the default Microsoft route to the internet, and instead use user-assigned route tables to route traffic via a VPN, network virtual appliance, or firewall. Control internet traffic, both inbound and outbound, using a network virtual appliance or Azure firewall. Implement restrictive network security group rules, which only allow that traffic that is absolutely essential. Use application security groups to simplify management of network security groups. Configure NSG flow logs, and enable Network Watcher and Traffic Analytics. Use an IPsec VPN or ExpressRoute to connect on-premise data centers with Azure. Ensure that your developers and administrative users connect to a Bastion server first, and then from there to virtual machines in Azure, or make use of Azure Bastion. And last but not least, restrict permissions using RBAC roles, and make use of privileged identity management. Virtual machines running production workloads in Azure should use hardened operating systems. Unneeded services should be turned off, permissions should be tightened, and insecure default settings changed. A great starting point for implementing secure operating systems is to use the Center for Internet Security, or CIS, benchmark for that operating system, whether it be Windows or a Linux variant such as Debian, Ubuntu, CentOS, or Red Hat. In all cases, the benchmarks have been developed by the security community and include a whole series of different controls to a high level of detail, the controls being classified either as Level 1, which is a base level of security, or Level 2 for those organisations with the most stringent requirements. In the case of Windows, an effective way to implement the CIS benchmarks is to use Active Directory Domain Services on IaaS, or the Azure Managed AD-DS, join the service to the domain, and implement group policy as a very effective way of applying the CIS benchmark requirements. In the case of Linux, a good starting point is to harden the image as much as possible, and then use tools such as Ansible, Chef, or Puppet to control the configuration. After implementing operating systems securely, whether that be on Windows or Linux, it's also important to continuously check the compliance on an ongoing basis. This can be achieved using tools such as Chef Enterprise or Qualys, in either case scheduling routine scans and audit reports to assess compliance against the CIS benchmarks. A common requirement in any cloud service, and that includes Azure, is for a virtual machine to be able to access resources, data and information from other cloud services. For example, a virtual machine might need to connect to a Cosmos DB database, or download a file from Azure Storage, or write to a logging system. So the question is, how does the virtual machine authenticate and prove that it is authorized to obtain that data, information or access on the other cloud service, even if it is within the same subscription? One way of doing this is to hard-code service principal credentials within the virtual machine, and then to run some script or program on the virtual machine to make use of those credentials, authenticate to Azure Active Directory, and obtain authorization to access the resources. But that's actually a really bad idea from a security point of view. The service principal credentials will be valid for 1 or 2 years. They could be stolen from the virtual machine, or the infrastructure as code used to build the virtual machine, and in either case, used by an attacker maliciously to obtain unauthorized access. Microsoft's solution to this is Managed Identity. Managed Identity is the creation of an Azure Active Directory identity for the virtual machine. It's assigned to the virtual machine and avoids the use of hard-coded credentials. Roles can be assigned to that identity, giving permissions, which are then used to access resources in Azure. For example, Azure Storage, Azure SQL, or Azure Cosmos DB. There are two types of managed identity, a system-assigned identity or a user-assigned identity. User-assigned identities can be useful if you want to pre-configure with a certain set of roles before the virtual machine is built. Let's take a look at an example. An application running on a virtual machine in Azure needs to read or write data from Cosmos DB. To do so, it first connects to the Azure metadata service and obtains an OAuth 2 token, which is valid for a period of time such as 1 hour. Having downloaded the token, the application then includes it within its calls to Cosmos DB. Cosmos DB checks the token for authorization and then permits access to its data. And now it's time for the Virtual Machine Security Lab. Ensure you've already completed the Network Security Group Lab and that you have a Windows virtual machine available. Select it. Remove any NSG rule or routes preventing outbound internet access. Add the Azure extension for Microsoft Anti-Malware, and then confirm Microsoft Anti-Malware is installed. If you'd like to take the challenge approach to this lab, then please pause the video now, go ahead and follow these steps, and when you're finished, you can compare how you did it with my walkthrough. If you prefer the guided approach, then I'll see you in the Azure portal now. So here we are in the Azure portal. Start by going to Virtual Machines, select your Windows virtual machine, make sure that it is running, then choose Extensions, Add, select Microsoft Anti-Malware, Create. We'll leave all of the defaults as they are, press OK. And deployment of the anti-malware extension has been completed. Let's refresh to view. Currently the status is shown as unavailable. And after refreshing the browser, we see that provisioning of the extension has now succeeded. The next step is to check that anti-malware has been installed. To do this, you'll need to remote desktop onto your virtual machine. So I'll see you on the Windows server. You've logged into your Windows server via remote desktop. Press Start. A new menu item should have appeared. Windows Security. Select that. And this indicates that Microsoft Anti-Malware has successfully been installed. Let's test it. Open Internet Explorer. Browse to https:// icar.org, icar spelt E-I-C-A-R. Download the anti-malware test file. Most straightforward way of doing this is to copy the string provided into your clipboard. Right-click, New text document. You can call it icar.txt. Paste in the test file and save. And we can successfully see that Microsoft Anti-Malware has identified iCar as a threat. Well, that's the end of this lab. You'll be doing more labs on Azure Virtual Machine Security later in this course. If you have any questions, please let me know. Otherwise, feel free to move on to the next lecture. Hello Cloud Gurus and welcome to this lecture on Update Management. Azure Update Management Solution provides system updates for Azure virtual machines, supporting both Windows and Linux. Before implementing, do check that the exact operating system versions you're using are supported. There's a link provided to the Microsoft documentation within the resources section for this lesson. For example, early versions of Windows Server 2008 only support update assessments. Various versions of Linux are supported, including CentOS, Red Hat, SUSE Linux and Ubuntu. And it's also important to be aware of certain types of client which are not supported. These include client operating systems such as Windows 7 and Windows 10, Windows Server 2016 Nano Server, and Azure Kubernetes Service nodes. Azure Update Management can support virtual machines both in Azure and on-premise. It makes use of a log analytics workspace. Update assessments can be conducted, alerts provided when updates are required, and update deployment can be scheduled. Finally, the administrator can view the results of an update deployment. Virtual machines managed by Azure Update Management use the configurations shown in this diagram to perform update assessments and update deployments. These include the Microsoft Monitoring Agent MMA for Windows or the OMS Linux agent. PowerShell Desired State Configuration, DSC, is used for Linux. An automation runbook account is an important element of the solution, and the automation hybrid runbook worker created for each virtual machine. Windows servers need to be able to access either Microsoft Update or Windows Server Update Services, WSUS. Update management can be used to natively onboard machines in multiple subscriptions within the same tenant. Once a package is released, it takes typically 2 to 3 hours for the patch to show up for Linux machines, and for Windows machines 12 to 15 hours. The computer completes a scan for update compliance, and then the agent forwards the information in bulk to Azure Monitor logs. On a Windows computer, the compliance scan is run every 12 hours by default. And you can also initiate this more quickly by restarting the MMA service. The Update Management solution links the Log Analytics workspace and automation account, and is used to view update assessments, install updates, and view update deployments. And now it's time for the Update Management Lab. Ensure you've already completed the Network Watcher Lab. Then create an Azure Automation account. Link the automation account with the Log Analytics workspace, which you should still have from the Network Watcher Lab. Add the Update Management solution. Connect the Windows virtual machine. View an update assessment for that Windows virtual machine. And then schedule an update deployment to install any needed patches, and view the results. If you'd like to take the challenge approach to this lab, then please pause the video now. Go ahead and follow these steps, and when you're finished, you can compare how you did it with my walkthrough. If you prefer the guided approach, then I'll see you in the Azure portal now. You've logged into the Azure portal. Begin by going to Virtual Machines, and just make sure that your Windows server is actually running. Having done that, select Automation. Before you create the Azure Automation account, just check out the supported mappings between Log Analytics workspaces and Azure Automation in different regions. In your case, you created a Log Analytics workspace in the East US region as part of the Network Watcher Lab. So your Azure Automation account needs to be created within the East US 2 region. Return to Azure Automation accounts in the portal. Create Automation account. Enter the name EUS2 Auto. Use the existing resource group. The location should be East US 2. Leave the Create Azure Run As account as yes, and create. The Azure Run As account has now been deployed. Go to the resource and select Inventory. Choose the Log Analytics workspace that you created as part of the Network Watcher Lab. In my case, that's App EUS LA, and enable. This may take up to 15 minutes, so I'll fast forward the video until that's complete. The change tracking and inventory solution has now been enabled. Return to the automation accounts and inventory to see details. Next, select Update Management and enable. The Update Management solution is now being deployed. This can also take around 15 minutes, so again I'll fast forward the video until it's complete. The update management solution has been enabled. This only took around 5 minutes in my case. Return to the automation account, select Update Management, and the solution has been successfully deployed. Now, add an Azure virtual machine. Choose the Windows Server and enable. The Windows virtual machine is being onboarded to Update Management. Again, this may take a little while, so once more I'll fast forward the video. You may find that virtual machine information doesn't show up straight away in this section of the portal under Automation Accounts, so instead head over to Solutions. Select your update solution. View the summary. At the current time, this machine is shown as compliant and up to date. However, this is probably just because it hasn't yet completed all of its internal scans. So wait a little while and come back, refresh the browser, and then take another look. Okay, so now that we've waited a little longer, we can see that the virtual machine does require updates. Let's select this to find out more details. And we can see that at least 3 updates are required. In your case, you may see something a little bit different from this. It will all depend on when you built the virtual machine, how up-to-date the image was, and when you did this assessment. Next, go back to the automation account and take a look at the hybrid worker groups, system hybrid worker groups, and you should see your Windows Server appear here. Then go to Update Management. In my case, the Windows virtual machine is now showing in this section. If yours hasn't appeared yet, you may want to just carry on with the next video on the course and come back an hour or so later to see if it's appeared. You can see details of any updates that are required for your virtual machine and schedule an update deployment. Choose a name for your update deployment. EUS Update 1. Leave the operating system as Windows. Select the machines to update. Select the updates category and OK. Leave the update classifications as all and select scheduled settings. I'd suggest you leave the default time, which will be fairly immediately, which is fine for a lab test. Leave the time zone as the default and recurrence as once. And then press OK. Then press Create. And the scheduled deployment has now been created. The update deployment should now be visible under Deployment Schedules within your virtual machine details. I'd suggest returning towards the end of the maintenance window. I'll fast forward the video until that point. Okay, after around 30 minutes, the update deployment has completed. You can check this by going to History, select the update deployment, and you should see a successful update run status and details of patches installed. Going back to the overview screen, as is often the case with Windows updates, now that we've installed a couple of updates, others are now shown as being required, and these will be added in a later update deployment. Well, that concludes the Update Management Lab. If you have any questions, please let me know. Otherwise, feel free to move on to the next lecture. Hello Cloud Gurus and welcome to this lecture on Azure Container Services. Docker is the leading operating system virtualization software, allowing applications to run in small packages known as containers. A container is everything needed for a piece of software packaged together. A full operating system isn't needed, only the essential libraries needed to run that particular application. Containers are efficient, lightweight, and self-contained. Application developers really like containers because the software that they're developing will run exactly the same regardless of where it is deployed. So they can start developing on a laptop and be confident that it will behave the same on a production server. The deployment is extremely fast, which means that the application development process in turn becomes faster and more efficient. If you want to know more about Docker containers, then take a look at the Docker Fundamentals course on aCloud Guru. I've provided a link to the course in the resources section of this lecture. This diagram shows an example of containerized application architecture using Docker. Towards the top of the diagram, each container consists of the application software and any essential binaries or libraries to support it. All of the containers sit on top of the Docker runtime, which in turn interfaces with the host operating system and the virtual or physical infrastructure underneath. There are three principal Azure Container Services, each of which we'll be looking at in more detail in later lectures. Azure Kubernetes Service uses containers which are running on dedicated virtual machines for each customer, managed by Microsoft. Container Orchestration uses the open source Kubernetes platform. Next up, Azure Container Instances, which allows customers to run containers without needing to be aware of the underlying virtual machines. And the third principal service is Azure Container Registry, which is a private registry for Docker container images that can be used with both Azure Kubernetes Service and Azure Container Instances. So that concludes this lecture on Azure Container Services. If you have any questions, please let me know. Otherwise, feel free to move on to the next lecture. Hello Cloud Gurus and welcome to this lecture on container security. We'll start by reviewing risks to applications and systems using containers and look at best practice controls to mitigate those risks. It's extremely easy to start and run a container. For example, type docker run busybox. That will download the busybox container image from Docker Hub and run it. But you've got no guarantees as to whether that busybox image is vulnerable or not. Bearing in mind that images include operating system libraries, they will become out of date and vulnerable. So the best practice is to vulnerability scan the container registry and make sure you're always using up-to-date versions of the images. Even more serious than vulnerable container images is the possibility that the container could be deliberately malicious. The best practice control to mitigate against this risk is to use private and/or trusted registries and Docker Content Trust for image signing. To reduce the risk of privilege escalation and host takeover, best practice is not to run applications within a container as root and not to allow containers to run in privileged mode. Use namespaces and role-based access control to separate different containerized applications running on the same host. Encrypt all inter-container traffic and implement effective secrets management. Finally, implement a container orchestration solution such as Kubernetes across multiple nodes so that if a single host fails, the application will still be available to users. Forrester has published a paper, 10 Basic Steps to Secure Software Containers. You can find the link for that in the resources section of this lecture. Forrester proposed a defense-in-depth approach to container security, as shown in this diagram. The container itself is built up of layers, starting with the base image, then the file system, application libraries, and the developed code. All of this is packaged up into a Docker container, which is then downloaded from the registry and then run within the container runtime environment alongside other containers as well. The container runtime environment sits on top of the host operating system. There's a user access layer, network segmentation between applications, and container orchestration. So, from a security perspective, all of the different aspects shown in this diagram need to be configured securely and kept up to date. Forrester's 10 basic steps to secure software containers are shown in this diagram across 3 different phases: develop, build, test, modify, and release to production. Use trusted images, reduce clutter, sign images and verify signatures, enforce effective secrets management, implement network segmentation, ensure user authentication, scan container images for vulnerabilities, harden the host operating system, govern operations, and implement intrusion detection. Now let's move on to container security within Microsoft Azure. Microsoft has published a paper on this topic. The link to this is in the resources section for this lecture. It's a white paper which includes a comprehensive introduction to containers, container security, and provides extra information on Azure Kubernetes service security as well. Let's take a quick look at Azure container instances. There's no servers to manage, they're internet facing, so generally they're not suitable for private applications where you want to control network access. Security considerations recommended by Microsoft include vulnerability management of container images, only permitting containers to run from approved registries, ensuring image integrity, and least privilege runtime. Azure Container Monitoring is recommended for use with Azure Container Instances. That concludes this lecture on container security. We'll be covering Azure Kubernetes security and Azure Container Registry security in later lectures. If you have any questions, please let me know. Otherwise, feel free to move on to the next lecture. Hello Cloud Gurus and welcome to this lecture on Azure Container Registry. Azure Container Registry is a managed private registry for Docker container images. It can be used with Azure Kubernetes Service, Azure Container Instances, or any other system running Docker containers. From a network perspective, it's reachable from the public internet using a fully qualified domain name, or FQDN. For example, if your container registry is called My Registry, the FQDN would be myregistry.azurecr.io. That's why the name of every Azure Container Registry has to be globally unique. So if you try and create one called My Registry, I think you'll find somebody else has already done it. There are two options for authentication to Azure Container Registry: access keys and Azure AD with role-based access control. We'll be looking at both of these later from a security perspective. ACR Tasks is a suite of features providing cloud-based container building for both Linux and Windows, and can be used to automate patching and updates of Docker containers. We'll now take a look at the security aspects of Azure Container Registry, starting with access control. Within Azure Container Registry, there's the option to enable the admin user. If you do this, two access keys are automatically generated, and then anyone with one of these keys has complete read-write access to the registry. From a security perspective, this is potentially a high risk, as anyone with this key could upload new container images which might be vulnerable or even deliberately malicious. So you should never enable the admin user in a container registry, unless you're using it purely for development and test purposes. The recommended approach to authentication and access control for Azure Container Registry is using Azure AD credentials with role-based access control. A user logs into Azure AD, and his or her permissions depend on the role. For example, the Microsoft built-in role ACR pull only allows download of images from the registry. Other built-in roles include ACR push, ACR delete, and ACR image signer. If another resource or service in Azure needs to access the registry, as opposed to a human user, this can be achieved either by using a managed identity or service principal as appropriate. Azure Container Registry has some useful premium security features, all of which require the premium pricing SKU. The firewall and virtual network feature can be enabled and used to specify which public IP addresses and Azure Virtual Network subnets are allowed to access Azure Container Registry. This is a great example of defense-in-depth security. If an attacker obtained credentials permitting access to Azure Container Registry, they still wouldn't be able to access confidential information via the public internet. Whenever possible, you should enable firewalls and virtual networks and configure them to only allow access from your relevant Azure Virtual Network subnets for that environment. Content trust can be enabled in Azure Container Registry. This makes use of Docker's content trust model, enabling pushing and pulling of signed images. As an image publisher, content trust allows you to sign the image you push to your registry, providing assurance that the images have been published by you and have not been modified. You can choose to sign certain container tags and not others. For example, you might choose not to sign containers with a development tag. Content trust is managed using a set of cryptographic signing keys associated with each repository within the registry and created locally on the administrator's machine. A passphrase is generated using Docker for each signing key and must be carefully protected along with those signing keys. Another premium feature of Azure Container Registry is geo-replication to another Azure region. This can be very useful either for disaster recovery purposes or to ensure the fastest possible launch time for new containers in different regions. And just a reminder that the premium pricing SKU is required for all of these features. And now it's time for the Azure Container Registry Lab. Start by creating an Azure Container Registry in the East US region, remembering that every registry must have a globally unique name which hasn't already been chosen by somebody else. For this lab you only need to specify the basic SKU. Clone or download the A Cloud Guru AZ-500 repository from GitHub A Cloud Guru resources. You'll find the link to this in the resources section of this lecture. Follow the detailed instructions in the Azure Security folder README. Log in to Azure from your laptop using Azure CLI. Use ACR tasks. Pull the Docker container A Cloud Guru Labs Cloud Vote, and then push that container image up to your Azure Container Registry. If you'd like to take the challenge approach to this lab, then please pause the video now, follow the instructions in the ACR Security folder README, and when you're finished, you can compare how you did it with my walkthrough. If you prefer the guided approach, then I'll see you in the Azure portal now. You've logged into the Azure portal. Begin by searching for container registries. Add. Enter a unique name for your container registry. In my case, I will choose Learn Security. That is available. Use the existing resource group. Leave the admin user as disabled and the SKU as standard. Press Create, and you may want to pause the video here until your deployment is complete. Okay, the deployment is now complete, so select Go to Resource. First, take a look at some of the features of Container Registry, beginning with access keys. As discussed in the lecture, it's not a good idea to enable the admin user because these passwords are created which anybody can use to obtain complete read and write access to your registry. Firewalls and virtual networks, as discussed, are a great feature. However, they do require the premium pricing SKU. Repositories are currently empty. Replications allow repositories to be replicated across different Azure regions. And Content Trust, another premium feature, enables you to digitally sign container images and push those trusted images to the registry. You're now ready to begin by uploading your first Docker container to your Azure Container Registry. Next, go to GitHub, A Cloud Guru -resources, and find the AZ-500 repository. Clone the repository. Git clone. You've cloned the repository. CD into the repository. And CD into the ACR-Security folder. Returning to the web browser, going into the ACR Security folder, the README outlines the requirements for the lab, which are a Windows 10 or Mac OS laptop. In my case, I'm using Mac OS. You'll also need Azure CLI and Docker. Start by logging into Azure using the CLI, either with PowerShell on Windows or Terminal on Mac. Type AZ login. Go ahead and log into the web browser. Once you're logged in with the browser, you will see details of your subscription. Next, log into your Azure Container Registry. Enter the name of your container registry. You're now logged into your newly created Azure Container Registry. Making sure you're already in the Azure Security folder, use this command. Enter your container registry name. And enter. The container is being downloaded from A-Cloud Guru's Docker Hub. Notice that the container, like most container images, consists of a number of layers. This can be very useful because if a change is made to a container, then that will only affect one layer, and only that new layer would need to be downloaded to update the container. This significantly speeds up container start times. You may wish to pause the video now until your upload is complete. Okay, the container has been downloaded from A-Cloud Guru's Docker Hub and uploaded to your private Azure Container Registry. Return to the Azure portal. In your container registry, select Repositories. You'll now see the CloudVote container and details of the version. Well, that concludes the Azure Container Registry Lab. If you have any questions, please let me know. Otherwise, feel free to move on to the next lecture. Hello Cloud Gurus and welcome to this lecture on Azure Kubernetes Service. Kubernetes is an open source system for automating the deployment, scaling and management of containerized applications. With Kubernetes, multiple containers can be managed as a single entity for high availability, scaling and networking. Originally developed by Google, Kubernetes is now maintained by the Cloud Native Computing Foundation. Kubernetes has been widely adopted and has now become the de facto standard for container orchestration. Google Cloud Platform, Amazon Web Services and Azure all offer managed Kubernetes services. For a more detailed introduction to Kubernetes, check out the A-Cloud Guru course, Kubernetes Deep Dive. You'll find the link to this in the resources section for this lecture. This diagram shows a typical Kubernetes architecture. A Kubernetes cluster distributes containers across multiple hosts known as nodes for high resilience and scaling. The Kubernetes cluster nodes are controlled from the Kubernetes master, which manages the cluster and directs communication across the system. The Kubernetes control plane includes etcd, a persistent, lightweight, distributed key-value data store, which allows containers to download key-value data. The containers, shown in pale green, are grouped into pods to allow close sharing of resources. The pods are deployed to nodes, or virtual machines, in a distributed manner. From a networking perspective, Kubernetes usually implements an overlay network so that the containers have a different network address space from the underlying virtual machine subnets. Access from external clients is provided via a Kubernetes load balancer. The operator or CI/CD pipeline communicates with the API server on the Kubernetes master using kubectl or kubecontrol, pronounce it as you prefer. That's a command line interface, and containers and services are defined as YAML files. Containers are pulled from images stored within a container registry. Azure Kubernetes Service is a managed Kubernetes service provided by Azure. The Kubernetes master providing core services and orchestration is fully managed by Microsoft with administrative access available via the kubectl command line. Kubernetes nodes are deployed by Microsoft to run the application workloads on dedicated virtual machines and maybe either Linux or Windows pools as specified by the customer. The best way of understanding Azure Kubernetes Service is to get hands-on with it, so let's dive straight into the Azure Kubernetes Service Lab. Make sure that you've already completed the Azure Container Registry Lab. Clone or download the AZ-500 repository from the GitHub A-Cloud Guru Resources Organization. Follow the detailed instructions in the AKS Security folder README. Create a service principal and record the client secret. Assign the ACR pool built-in role at the subscription level. Create an AKS cluster using the Azure CLI. Log in to the AKS cluster using kubectl. Modify the CloudVote YAML file, and then deploy the CloudVote application to your cluster and test. If you'd like to take the challenge approach to this lab, then please pause the video now, follow the instructions in the AKS Security folder of the AZ-500 repository, and then when you're finished, you can compare how you did it with my walkthrough. If you prefer the guided approach, then I'll see you in the Azure portal now. You've logged into the Azure portal. Begin by going to the GitHub AZ-500 A-Cloud Guru resources repository and enter the AKS Security README for information. Prerequisites are the completion of the Azure Container Registry Lab and requirements Windows 10 or Mac OS and Azure CLI. Open PowerShell for Windows or Terminal for Mac. You should still have the cloned repository, but if not, just clone it now, and then cd into the repository. From there, cd again into AKS-Security. Log in to Azure. Once you're logged in, you'll have details of your subscription and your logged in user. Return to the web browser. Next, copy the command to create a service principal and assign role. Return to the terminal or PowerShell and enter the command. The service principal has been created. Copy the details and paste them into a text editor. Return to the browser. Next, create your AKS resource group. You've created your Azure Kubernetes Service resource group. Going back to the browser again. If you copy the next command, paste it in, and then replace the app ID with your client ID in quotation marks. Grab your client secret. Enter the client secret to the command and enter. Your Azure Kubernetes service cluster is now being created, so you may want to pause the video now until it's complete. Okay, the Kubernetes cluster has now been deployed. That took around 5 to 10 minutes in my case. Let's return to the repository. Just to recap, you created a service principal, assigned the built-in ACR pool role, then you created a resource group in the East-US region, specifically for Azure Kubernetes Service, and you created the Azure Kubernetes Service cluster with just one node and provided details of the service principal with the ACR pool role. Return to the portal to take a look. Search for Kubernetes. You'll now see your Azure Kubernetes service. Going to Resource Groups, you'll see that in addition to the new resource group which you created containing the Kubernetes service, Microsoft has also automatically created its own resource group containing the pool. In this case, there's just the one Linux virtual machine and associated networking components. Going back to the README file, the next stage is to install kubectl if running locally. If you're installing on a Linux or Mac environment, use sudo AZ-AKS install CLI. Okay, that took a few minutes to install. Return to the README. The next command is to obtain administrator Kubernetes credentials from your Azure Kubernetes Service Master. kubectl credentials have been obtained. To verify the connection, type kubectl get nodes. This will list the virtual machines within the Azure Kubernetes Service node pool. In this case, there's only one node. Next, type kubectl get namespaces. Namespaces are a way of dividing areas and applications within an Azure Kubernetes Service cluster. There's a default namespace and two Kubernetes namespaces, which were automatically created when you deployed your Azure Kubernetes Service cluster. Next, type kubectl get pods. This lists containers running within the default namespace. Of course, there aren't any, as nothing's been deployed yet. Now type kubectl get pods dash dash namespace kube system. You will now see all of the containers which run as part of the Kubernetes service cluster itself. And now it's time to install your own application. Go to your code editor, add the AZ-500 repository folder to your workspace, expand the AKS Security folder, select the cloudvote.yaml file, go down to line 51, replace your Azure Container Registry name with your own name. In my case, that's Learned Security, and save. Return to your command line. Make sure you're in the AKS Security folder. Type kubectl apply -f cloud-vote.yaml. The application is being deployed to your Azure Kubernetes Service cluster. You can see that there are two containers, the Azure Vote back and the Azure Vote front. To monitor progress, type kubectl get service Azure-vote-front -- watch. The external IP has now been assigned. You can cancel out of the watch command. Take a look at your pods by typing kubectl get pods. There are now two containers running in your default namespace, the Azure Vote back and the Azure Vote front. Copy the external IP address, go to your browser, add a new tab, paste in the IP address. You've now deployed your first application to your Azure Kubernetes Service cluster. Vote for your favorite cloud, Azure or AWS. And when you're finished, just press the reset. After you're finished voting, return to the README. Copy the command to authorize the Kubernetes dashboard. And enter. Next, copy the command to view the Kubernetes dashboard. This will open up your default browser. You've now opened the Kubernetes dashboard with details of deployments, pods, replica sets, services, and any secrets. There's one more thing you need to do, and that's tidy up. Return to the command line, copy and paste the command from GitHub, or type AZ, delete, and then details of the name of the Kubernetes cluster and resource group. Then press enter. Confirm you want to perform the operation, and your Hello Cloud Gurus, and welcome to this lecture on container vulnerability management. Vulnerabilities in containers are a significant risk. To be effective, Hello Cloud Gurus, and welcome to this lecture on kubectl get pods. You will now see all of the containers which run as part of the Kubernetes service cluster itself. And now it's time to install your own application. Go to your code editor. Add the AZ-500 repository folder to your workspace. Expand the AKS Security folder. Select the cloudvote.yaml file. Go down to line 51. Replace your Azure Container Registry name with your own name. In my case, that's Learned Security. And save. Return to your command line. Make sure you're in the AKS Security folder. Type kubectl apply -f cloud-vote.yaml. The application is being deployed to your Azure Kubernetes Service Cluster. You can see that there are two containers, the Azure Vote Back and the Azure Vote Front. To monitor progress, type kubectl get service Azure-vote-front --watch. The external IP has now been assigned. You can cancel out of the watch command. Take a look at your pods by typing kubectl get pods. There are now two containers running in your default namespace, the Azure Vote Back and the Azure Vote Front. Copy the external IP address, go to your browser, add a new tab, paste in the IP address. You've now deployed your first application to your Azure Kubernetes Service Cluster. Vote for your favorite cloud, Azure or AWS. And when you're finished, just press the reset. After you're finished voting, return to the README. Copy the command to authorize the Kubernetes dashboard. And enter. Next, copy the command to view the Kubernetes dashboard. This will open up your default browser. You've now opened the Kubernetes dashboard with details of deployments, pods, replica sets, services, and any secrets. There's one more thing you need to do, and that's tidy up. Return to the command line, copy and paste the command from GitHub, or type AZ, delete, and then details of the name of the Kubernetes cluster and resource group. Then press enter. Confirm you want to perform the operation, and your Azure Kubernetes service resource has now been deleted. Next, type AZ group delete, and then the name of the resource group, and --yes to confirm. This may take a few minutes, so feel free to pause the video until it's complete. Okay, well that took about 10 minutes in my case. Your Azure Kubernetes service resources have now been destroyed. And that concludes the Azure Kubernetes Security Lab. If you have any questions, please let me know. Otherwise, feel free to move on to the next lecture. Hello Cloud Gurus, and welcome to this lecture on Azure Kubernetes Service Security. AKS Security includes native Kubernetes security controls and features, as well as integrations with other Azure security services. We'll start by exploring the integration of AKS with Azure AD, limiting access to the API server, and the use of pod identity. Then we'll move on to review AKS network security, and the optional addition of other Azure services, such as Application Gateway and Web Application Firewall. We'll cover native Kubernetes security features, including Kubernetes network policies, options for Kubernetes secrets, content trust, Helm charts, AppArmor, and pod security policies. Finally, we'll look at how to keep your Kubernetes platform up to date. There's a very good Microsoft Ignite talk on AKS security, with live demos of some of these features, which I can highly recommend. You'll find the link in the resources section of this lecture. To manage a Kubernetes cluster, you use kubectl, a command line client which connects remotely to the Kubernetes master. By the way, kubectl can also be pronounced kubectl, depending on your preference. Once you've logged into Azure CLI with your Azure AD credentials and have network connectivity to the Kubernetes master, you can use the AZ-AKS get credentials command. If you have the Azure AD Kubernetes Service Cluster Admin role, you can obtain Cluster Admin credentials. If you have the Azure AD Kubernetes Service Cluster User role, you can obtain Cluster User credentials. Either way, the credentials are downloaded to your local machine. This can potentially be a security risk, as credentials could end up on any machine with connectivity to the Kubernetes master. From a security perspective, it's important to limit who is assigned these built-in roles. Access to the API server used for the kubectl service can be limited to authorized IP address ranges. This is a great example of defense in depth. Even if an attacker obtained your Kubernetes administrator credentials, they wouldn't be able to connect over the public internet to use them. Containers running on AKS may well need to access other resources in Azure, such as a storage account or key vault. To enable this, they can be assigned an Azure pod identity. This is a managed identity within Azure AD, similar to a virtual machine's managed identity, but in this case assigned to the Kubernetes pod. The pod identity can then be assigned Azure resource roles to control access. Here's an example. On an AKS cluster node, there are two pods. We assign a pod identity to pod 2. One of the apps running in pod 2 obtains the pod identity token from Azure AD. It then presents the token to other Azure services, such as a storage account or Cosmos DB, to authorize access, depending on permissions. Pod 1, on the same cluster node virtual machine, hasn't been assigned a pod identity and so cannot access Azure resources. There are two different ways to deploy Kubernetes clusters into Azure networks. KubeNet networking, which uses the Kubernetes plugin to provide a virtual network address overlay, and Azure CNI, CNI being an abbreviation for Container Networking Interface, where pods receive individual IP addresses which can route to other network services or on-premise resources. For production deployments, Microsoft recommends that you use Azure CNI networking, which lets you connect to Azure resources or other services directly via IP addresses assigned to every pod. Azure CNI is required if you want to install your AKS cluster within a VNet. Kubernetes network policies can be used to control the flow of traffic between pods. They're defined by YAML files and implemented using kubectl. In the example shown, access to pods with the backend label is only allowed from pods with the front-end label. Traffic can be allowed based on Kubernetes namespaces, as well as pod labels. Network policies need to be enabled when the AKS cluster is created. Kubernetes network policies can be defined either using Azure network policies or Calico network policies, and in either case are implemented using Linux IP tables, and require the Azure CNI network option. As they use Linux IP tables, they can't of course be used for Windows Server pools. Microsoft recommends the use of Kubernetes ingress controllers to distribute traffic across containers within the Kubernetes cluster. That's the standard approach when using Kubernetes. Typically, an Nginx container is used to terminate the traffic, which is then balanced across pods throughout the cluster. For internet-facing web applications, it's best practice to use an external application gateway, which terminates the TLS. A web application firewall, or WAF, provides an additional layer of security by filtering the incoming traffic. The Azure Web Application Firewall integrates directly with the Azure Application Gateway, which also provides the benefit of distributed denial of service protection. Azure DDoS protection has two service tiers. The basic tier is automatically enabled as part of the Azure platform and includes always-on traffic monitoring and real-time mitigation of common network-level attacks, providing the same defenses utilized by Microsoft's online services. The standard tier provides additional mitigation capabilities, machine learning algorithms, improved reporting and metrics, and access to the Microsoft DDoS response team. Using this architecture, network addressing of the AKS cluster can be kept entirely private within the VNet, and optionally, an internal Azure load balancer can be used as well. Other Azure Kubernetes Service security features include the Kubernetes Secret Store for key value pairs. While this is one approach, another option is the use of Azure Key Vault combined with pod identity. Content Trust only allows signed images to run, providing assurance that an image has been published by the authorized owner. This fits in nicely with the Content Trust feature of Azure Container Registry. Helm charts can be used as a way of managing and controlling deployments of containerized applications at scale. AppArmor is a Linux kernel security module which restricts access to sensitive Linux locations and is specified in the Kubernetes YAML manifest. Pod security policies can be implemented to control the nature of containers allowed to run within a Kubernetes cluster. For example, containers running as root or containers using privileged mode can be blocked. Kubernetes, like any software, needs to be kept up to date to take advantage of new features and to resolve any bugs or security issues. Microsoft supports the last 4 minor versions of Kubernetes at any time, and it's the customer's responsibility to ensure that their AKS cluster is maintained in a supported state. Upgrade AKS regularly using the AZ-AKS upgrade command. Patching of node pools is a combined responsibility between Microsoft and the customer. AKS automatically downloads and installs Linux security fixes. However, it's the customer responsibility to reboot Linux nodes when needed. Windows servers in Kubernetes cluster pools can be effectively updated by clearing a Windows node of running containers and then replacing the cluster node with the updated version. That concludes this lecture on Azure Kubernetes Service Security. If you have any questions, please let me know. Otherwise, feel free to move on to the next lecture. Hello Cloud Gurus, and welcome to this lecture on Container Vulnerability Management. Vulnerabilities in containers are a significant risk. To be effective, vulnerability scanning is needed for both container images stored within a registry and the actual containers that are running in a system. There's no native Azure service for container vulnerability management, so we need to use Azure Marketplace vendors. The two leading vendors for this technology are Azure Security and Twistlock. Features for both Azure Security and Twistlock include container registry vulnerability scanning, network discovery, segmentation and controls, intrusion detection and prevention, container security configuration assessment, and compliance reporting. I'm now going to give you a demonstration of container vulnerability management using Azure Security. The reason that I'm doing this as a demo rather than a lab is that to do this yourself, you'll actually need to obtain an evaluation license key from the vendor. I've created an Azure container registry, and I've uploaded a whole load of container images. I've installed Azure Security on an Azure Kubernetes service cluster. I've logged in to the dashboard, and we can immediately see that we have a whole load of information on running containers, container images that aren't registered, the hosts, and vulnerabilities. We can have a look at the various vulnerabilities for each of the different containers running on the system. If we take a look at one of them, Cloud Vote, we have 8 high vulnerabilities, 35 medium, no lows, and 206 informational. I can drill down into those by looking at vulnerabilities within this particular image, and for each of the various vulnerabilities I can see all of the details and recommended fixes. Moving to workloads, we have a breakdown of security issues against different Kubernetes namespaces, and if I select topology, we can get a view of the various containers running on Kubernetes and how traffic flows between them. Looking at vulnerabilities, we have a complete list of all the vulnerabilities across all of the container images on the system, ranked from high to medium to low. We have the ability to set policies to only allow approved containers to run or reject those with vulnerabilities. Moving to compliance, Azure Security undertakes a real-time assessment against Center for Internet Security benchmarks for both Docker and Kubernetes. In this demonstration, I've only scratched the surface of Azure Security's capabilities, and similarly, Twistlock is a very full-featured and comprehensive security product. If you want to know more, I'd encourage you to visit their websites. Links are provided in this lesson's resources. If you have any questions, please let me know. Otherwise, feel free to move on to the next lecture. Hello Cloud Gurus, and welcome to this lecture on Azure Resource Manager. Azure Resource Manager is the deployment and management service for Azure. It provides a management layer that enables you to create, update, and delete resources in your Azure subscription. You use management features like access control, locks, and tags to secure and organize your resources after deployment. When a user sends a request from the Azure portal, Azure PowerShell, Azure CLI, or directly from a REST client via APIs, the Azure Resource Manager receives the request and checks the authentication and authorization of that request. Azure Resource Manager then routes the request to the relevant Azure service, which takes the requested action. All requests are handled through the same API, shown by this small blue pale circle in the diagram. So you should always see consistent results whichever Azure tool you use. It's important to become familiar with key resource manager concepts. A resource is a manageable item which is available in Azure. For example, a virtual machine or a storage account, web apps or databases or virtual networks. A resource group is a collection of related resources making up an Azure solution, which you want to manage as a group. A resource provider is a service supplying Azure resources. For example, Microsoft.compute supplies the virtual machine resource. Similarly, Microsoft.storage is used to create and configure storage accounts. An Azure Resource Manager or ARM template is a declarative file in JSON format which defines one or more resources to deploy to a resource group or subscription in a consistent and repeatable manner. Declarative means that you state what you want to create without having to worry about the detailed sequence of each command or API call. Roles can be applied at 4 levels of scope within Azure. Management groups are collections of subscriptions and allow organizations with large numbers of subscriptions to group them and manage them efficiently in a consistent manner. For example, a company might have a development and a production management group, each containing several subscriptions. Application developers might have a high level of privilege within subscriptions in the development group, but much more restricted permissions within production ones. The next level down from management groups is subscriptions, then resource groups, and finally individual resources such as a virtual machine, virtual network or key vault. Lower levels always inherit settings from higher levels of scope. There are three fundamental Azure resource roles. The owner role allows all actions, including assigning rights to others. The contributor role allows nearly all actions, but you can't grant rights to other users. The reader role provides read-only access. Azure resource role assignments at a subscription level can be viewed in the portal at All Services, Subscriptions, Access Control, Role Assignments. Microsoft provide a large number of built-in roles, as well as the three fundamental roles, owner, contributor, and reader. Roles are collections of actions which are grouped together, typically representing a common job function or a requirement for an application. For example, the ACR pull role allows images to be pulled from the Azure Container Registry, but no other actions. The ACR push role has greater rights, allowing both pull and push actions for Azure Container Registry. You can view all the available resource roles in the portal at All Services, Subscriptions, Access Control, Roles. When deciding which roles to use, their scopes and assignments, it's important to strike a balance between the security principle of least privilege and ease of management. Let's take a look at some examples. An organisation wishes to allow access to auditors. The built-in resource role chosen is the security reader role, and it's assigned to the auditor group in Azure AD. The scope is the production subscription. This role assignment is a good example of least privilege, as it's effectively read-only access, and it's assigned to the auditor group rather than a single individual, so it should be straightforward to manage as and when new auditors come and go. The organisation has an application which needs to read and write data to a storage account. The built-in role Storage Blob Data Contributor is assigned to the application service principal. The scope is the storage account resource group, which contains several different storage accounts. This role is another good example of least privilege, provided that all the storage accounts in the group are relevant to that application. Isabella Anderson is an application developer in the organisation. She's been assigned the owner role, with the scope being the development management group, which includes several different Azure subscriptions, all used for application development. Well, this role assignment doesn't look so good. It's assigned to an individual rather than a group, which means it could lead to a large number of role assignments to manage. It's the owner role, so Isabella has complete rights to the subscription, and she's even able to make other people owners. It also seems overly broad, as Isabella's probably only working on one application, so it could well be that she's been granted rights to subscriptions for which she doesn't actually need access. This concludes the lecture on Azure Resource Manager. If you have any questions, please let me know. Otherwise, feel free to move on to the next lecture. Hello Cloud Gurus, and welcome to this lecture on custom roles. If the built-in